Once again, I welcome you all. Students, in the last class we have discussed about the stoichiometric defects and its type. In today's class, we will discuss about the non-stoichiometric defects and its type. So let us start today's class. Non-stoichiometric defect. Non-stoichiometric defects are the defects which arises when the ratio of cation and anion is different as represented by its chemical formula. Or we can say when the stoichiometry of a crystal is getting disturbed. Let us understand this with the help of an example. Suppose if you are having the crystal of NaCl in which Na plus is the cation and Cl minus is the anion. Now if I say that the ratio of cation and anion is 6:6, it means the stoichiometry is maintained here. Now if I say that the ratio of cations to that of the anion is 5:6, it means the stoichiometry is getting disturbed here. And this type of defect gives rise to a non-stoichiometric defect. Okay, now non-stoichiometric defects are of two types. The first one is the metal excess defect and the second one is the metal deficiency defect. Metal excess defect is again caused by anion vacancy and by the presence of extra cation in the interstitial sites. Metal deficiency defect is due to the removal of metal cation from its lattice site. Let us understand all these things in details. The first one is the non-stoichiometric defect. Just now I explained to you, non-stoichiometric defect is caused when the ratio of cation to that of anion is different as represented by the ideal chemical formula. This type of defect is called as non-stoichiometric defect. Now non-stoichiometric defects occur due to the metal excess defect, or the types are, the first one is the metal excess defect. Now metal excess defect, as the name suggests, that the metals or the positive ions or the cations are more in number. Okay. Now in metal excess defect, the cations are more than that of the anion and this gives rise to a metal excess defect. Now the metal excess defect is caused due to the anion vacancy. First we will discuss about this and the next one we will discuss in the next slide. So the metal excess defect due to anion vacancy. Now what happens in this case? In this case, a negative ion or an anion is missing from its lattice site, creating a hole over there. Now in order to maintain the electrical neutrality, the electron is being trapped in that hole. Okay, so to maintain the electrical neutrality. Now you can see in this figure that A plus represents the cation and B minus represents the anion. Now an anion is missing from its lattice site and that site or that hole is occupied by a negatively charged electron. Now this is so because here the electrical neutrality has to be maintained. It means that the total number of positive charge must be equal to the total number of negative charge. Then only the electrical neutrality is maintained. But you can say here that the A plus ion is more than that of the B minus ion. Or I can say that cations are more in number than that of the anions. So this here the stoichiometry is again getting disturbed. So this is called as your non-stoichiometric defect, which is due to the anion vacancy. Okay. Now here students, just see that the electron which is trapped by the anion vacancy is called as F center. Here F stands for Farben-Center, which is a German name. It means the color center. Now this F center is responsible to impart the color to a crystal. Right? So let us understand this with the help of an example. Suppose a sodium chloride crystal is there. And if we are heated the sodium chloride crystal by passing sodium vapors. Now the sodium atoms of the sodium vapors get deposited on the surface of the sodium chloride crystal. After that, the chloride minus ion or the Cl minus ion from the crystal lattice move to the surface and combine with the sodium atoms and form sodium chloride, NaCl. Now during this formation of NaCl, the electrons which are liberated by the sodium atoms then diffuse back to the crystal and occupies the anionic site which is created by Cl minus ion. Understood? Now, this electron is responsible for imparting a particular color to the NaCl crystal, which is yellow color. Now the question arises that how is it possible that the electron imparts color to a crystal? See students, we have already learned in previous class 11 that an electron, after absorbing energy, it moves to the higher energy state, okay, or excited state. Since the excited states are highly unstable, the electron has to come down to the lower energy state or the ground state. While coming down to the lower energy state, the electron emits energy in the form of heat and light. And that light shows a particular color to the crystal. In case of sodium chloride, it shows yellow color. In case of lithium chloride, it shows pink color. And in case of potassium chloride, it shows violet color. This is very important. You have to remember these colors. Okay. Now, again I am telling you, these F centers are responsible for imparting color to a particular crystal. Now, what are these F center? Electron trapped by the anion vacancies are called as F center. Now, from this defect, some of the physical properties are also changed. So, first one is that due to the free electrons, it shows some conductivity in the crystal. Second point is that you can see that the total number of positive ions are more than that of the anions, and one anion is missing from the lattice site. It means the density of the crystal is decreases here. Now, can you tell me that this type of defect is similar to which kind of defect? Yes, it is similar to that of the Schottky defect, because in Schottky defect also the density decreases, right? The third point is that it shows the paramagnetic nature. Paramagnetic nature is due to the presence of unpaired electron. You have already learned these things in your previous class. Diamagnetic nature is due to the presence of paired electron, and paramagnetic nature is due to the presence of unpaired electron. So this is all about your metal excess defect due to the anion vacancy. Let us see the next one. F center, just now we have discussed. This is again very important. That's why again here it is given. F center, again I am repeating, F centers are the center in which the electrons are trapped by the anion vacancy. Okay, the anions are missing from its lattice site, and that site or that hole has been occupied by the unpaired electron, and that F center is responsible for imparting the color to the crystal, right? So these are called as F center. The next metal excess defect is due to the extra cation present in the interstitial sites. Now see, metal excess defect due to the presence of extra cations in the interstitial site. Now in this type of defect, what happens that a extra cation is present or occupy the interstitial site. Now again, to maintain the electrical neutrality, an electron is present in its neighboring interstitial site. As you can see here in this figure, that A plus is present it occupies an interstitial site. At the same time, a negatively charged electron is also present in the neighboring interstitial site. Now, if we see this crystal lattice, we found that the total number of positive ions are again more here. Okay, so it means total number of positive ions are more than that of the negative ions. It means the stoichiometry is again getting disturbed here. But the electrical neutrality is still maintained because the total number of positive charge are equal to the total number of negative charge, right? So can you tell me that this type of defect is similar to which kind of defect? Yes, it is similar to that of the Frenkel defect, because in Frenkel defect also we have seen that the cations have occupied the interstitial site. The same happens in this case also, right? Now see the example here, it is given that zinc oxide. Zinc oxide is normally white in color at room temperature. But when zinc oxide is heated, it gives Zn2 plus ion plus a half O2 with the liberation of 2 electrons. Now this excess of Zn2 plus ion occupies the interstitial sites in a crystal lattice. And to maintain the electrical neutrality, these two electrons also occupy the neighboring interstitial site. So overall the electrical neutrality is maintained, but the stoichiometry is getting disturbed because the number of cations are more than that of the anions. I think this is now clear to you. Now let us move on to the next. Metal deficiency defect. Again, as it is clear from the name only, that metal deficiency, that there is a deficiency of metal atoms or deficiency of cations. Okay, so in this type of defect, what happens? A metal ion or a cation is missing from its lattice site, and a cation having a higher charge is present in the neighboring site. Students, this defect is generally found in the transition metals. Transition metals are having a very unique property that they shows the variable oxidation state, or they shows the variable valencies. Just like iron, Fe, it shows valency of +2 as well as +3. So in this type of defect, what happens? Particular cation having a charge lesser is missing from its lattice site, and at the same time a cation having the charge higher than the other one or the previous one is present in the another lattice site. Now you can see here that a vacancy is being created. A cation is missing from its lattice site. Okay, so in this case the number of cations are lesser than that of the number of the anions. So this gives rise to a metal deficiency defect. Again the stoichiometry is getting disturbed, but the total number of positive charge is again equal to the total number of negative charge. So the compound is electrically neutral. Okay, so the very important thing is that metal deficiency defects are found in the metals of transition elements, right? So this is called as metal deficiency defect. So this is all for today's class. I hope the topics are clear to you. If you are having any doubt, you can ask me. Okay, thank you students.